We're going to continue on here. We are talking obviously about titrations, and we talked about some different types of titrations and really the calculations along the way. We talked about strong acid, strong base titration. We also saw a weak acid, strong base titration. In each of these cases, we were having the base up in the burette and we were adding it to the acid, either the strong acid or the weak acid. We talked about the titration curves. And again, we have pH and volume of base added. And typical titration curve does have this sort of S type shape, like hopefully most of you got the other day. We do have our equivalence point. And remember that pretty much in all these type of titrations, there's really four different sort of spots to the titration curve that we're typically interested in. The first part's really before we start the titration. In the case of a strong acid and strong base titration, the only type of acid you have in your beaker is a strong acid, which means that you do have the H plus concentration and you could go really directly into the pH. You could actually just do it with the molarity as you have not added any base to it. So you don't have to worry about moles or anything like that. The next sort of spot on the titration curve is from the beginning of the titration to just before the equivalence point. And in this type of titration, as we talked about, you do need to do one ice table. That ice table does need to be done in moles as you're adding volume at this point. Really, the purpose of this ice table is to figure out how much strong acid you'll have left based on where you stop your titration. And you do want to, as we talked about a couple of times there, you do want to do that first table in moles and good practice afterwards to convert everybody back into molarity, again, using the total volume, the volume of acid you started with, and the volume, obviously, of base that you added up to that point. At the equivalence point in this type of titration is sort of the third part. And in a strong acid, strong base titration, remember, basically the equivalence point is the point where all the moles of the acid will equal the moles of the base. So you really will not have any of the strong acid or strong base left over. You basically will have a salt and water. And the salt that comes from this is a salt that basically comes from a strong acid and strong base. And as we talked about with hydrolysis, because they do come from a strong acid or strong base, they will not go through hydrolysis and they're considered a neutral salt. So you would expect the pH here to be 7 in terms of this type of titration. Again, because it should always just yield you a salt that will not go through hydrolysis and is neutral. The fourth part of the titration curve there is after the equivalence point. And after the equivalence point, you do need to do an ice table. In this case, though, there is sort of a switch that happens because you've gone past the equivalence point. The moles of the base that you're adding are definitely going to be more than the moles of the acid you started with. And because of that, you're going to do this ice table, and you should end up basically with two things at the end of this table. You should end up with a neutral salt, and you also should end up with some strong base left over. And because you do have that strong base left over, that's going to be the major contributor to the pH at this point. You want to convert those moles back into molarity using the total volume. That's going to allow to give you the OH minus concentration, which will get you the POH, and then you could get the pH from it. So again, these are the four sort of distinct areas of this titration curve, and that was specifically for our strong acid, strong base. Our weak acid strong base titration, like the one you did the other day, will look very similar in terms of the graph here. We will still get sort of that S shape. And we still have the sort of 4 points on this particular titration. Difference here, though, is really what we're starting with and what we sort of generate through this titration. At the very beginning, before you start titration, because you have not added any base at this point, you're basically just sitting with a weak acid. So it really is just a Ka type of problem at this point. It's a weak acid problem where you can use, again, the molarity at this point because you have not added any volume. It's going to be just a basic Ka problem with some x's. You're going to solve for x. X is going to be the concentration of H plus in this case, and that's going to allow you then at that point, obviously, to calculate the pH. You could do an assumption if it works. If the assumption doesn't work, then obviously quadratic would be what you would probably need to do there. Probably, as I mentioned maybe before, in these cases, you probably will not get like a perfect square on both sides. So that's going to be kind of your two options in terms of solving it. Now, once you start the titration here, and again, before the equivalence point, you will need one ice table. And the result of this ice table is you're going to use up the strong base that's added because you'll have more moles of the acid you started with. The result of this is you will make the conjugate base to that weak acid, and that means you also will make a buffer here. So at the end of this first table, you should pretty much hit a buffer. As a result of that, you again can convert it back into molarity by using the total volume. Once again here, you do have actually two options as to how to get to the pH. Because it is a buffer, you can probably, and probably the best bet would be to go just right into the Henderson-Hasselbalch equation, and you could calculate the pH. If not, again, as we talked about before, you could choose to do a second ice table rather than the Henderson-Hasselbalch. And again, the importance of doing that ice table, as we talked about a number of times, you do need initials on both sides. The weak acid and the conjugate base does need an initial concentration. Otherwise, you're really not doing a buffer sort of calculation. As we also talked about, you will blow through that buffer as you reach the third part of our titration over here, which again is the equivalence point. The difference at this point is you still will be using up all of your weak acid and your strong base at this point. You will again still be left with a salt and water. The main difference is that salt does come from a weak acid. So the part of the salt that comes from the weak acid, you would expect to go through hydrolysis, and you would expect it to be the conjugate base, which means when it reacts with water, it's going to accept the H plus from water, and that's going to produce hydroxide. And we would expect the equivalence point here to be basic because of that. You will basically produce a basic salt. And this does require you at the equivalence point here to actually do a double ice table. First ice table, really the whole purpose of it is to figure out what is the concentration of your salt. The second ice table is then to use that concentration you got from the first table and do a hydrolysis problem where the salt reacts with water and will produce hydroxide. A couple of things like normal hydrolysis type problems you do want to be careful of, and people always screw up on is, again, is producing hydroxide, so it should be basic. You will probably be given the Ka value in this type of titration, not the Kb, but you will need the Kb value here, right, to do the problem. And when you do solve for X in this table, remember it is not the H plus concentration, but it is the OH minus concentration. That's going to get you to POH and then to the pH. So sort of a double ice table shot right there at the equivalence point. Then we lastly talked about what happens after the equivalence point. Once again, much like the other titration, you're dumping in excess amount of sodium hydroxide or a strong base. In this particular example, that means that when you're done with that ice table, which should again be done in moles, you will have two things left over. You will have the salt that will go through hydrolysis and act as a base, but you also have a strong base left over, like sodium hydroxide. And out of the two, sodium hydroxide, for example, is a much stronger base than any salt that's going to act as a base. And it's going to be the major contributor to the pH because all it simply needs to do is let go of its OH when it goes for a swim. And that means at this point in the titration, as we talked about, we ignore the contribution of the salt and we look really at the strong base. And that again will give you the OH minus concentration to get you to the POH and then to the pH. Any questions on that? It was two different types of titrations here. Again, as we talked about before, it's important to know sort of where you're at in the titration because it can really help you with the calculation. Again, with a weak acid, strong base, basically at the beginning of a Ka problem, before the equivalence point, it's a buffer problem, hydrolysis problem at the equivalence point, and past the equivalence point, it's really just a strong base type problem. So if you have an understanding where you're at, you should kind of know what type of problem you need to do before you actually calculate it, which obviously can make the calculation much, much easier. Any questions on any of that stuff there from last time? All right, then we're off to the final looking titration curve here. And this is a titration of a strong acid and a weak base. The setup here is a little bit different. In this case, we actually have the strong acid up in the burette, and we're adding the acid to our weak base. So we got the base down below, and we're adding the acid. That is also why when you look at the titration curve here, it's upside down, because we are starting with a base and we're adding acid, so the pH is actually going to drop. And we still see a similar type of S curve, just kind of upside down. We also see a drop in the pH to the equivalence point and so forth, just like we see a rise in the pH when we're adding base in this case. Probably no surprise here. We're going to have the same 4 spots we got before we start the titration, before the equivalence point, at the equivalence point, and obviously after the equivalence point are our 4 spots here. So again, in this situation here, we would have the hydrochloric acid up on top, and here we would have the ammonia, which is our weak base, on the bottom here. And we're adding, again, acid to base in this case. So just like before, let's go through the 4 different parts here and see what's happening at each of them. So obviously at the very beginning, before we start the titration, we basically just have a beaker or a flask sitting there with a weak base basically in there. And since this is a weak base, this is basically just going to be a KB type problem, where you would take your weak base and do a little ice table action with it. Right. Where it's going to accept the H+, going to make a little NH4+, and some OH-. You could actually keep them together if you want, but we'll separate them. And this is going to be a normal ice table. Once again, we haven't really started the titration, so we haven't changed any volume. So this is going to be the molarity 0, 0, change minus X, plus X, plus X. And then obviously here, molarity minus X, X, and X. This can go into our KB expression. We will solve for X. And again, a reminder that this is a base. So when we do solve for X, it is the hydroxide concentration, not the H+. So that's going to take you down the POH route and then to the pH route. Again, you can make your assumption and see if it works and all those good stuff like we've done before in a weak base type situation. Any questions up there? Okay, so now that we've started our titration, we are going to be now at sort of our second spot here. We're going to start to see our pH start to come down as we start adding. So just like before, once we start our titration before the equivalence point, we are going to get a reaction that's going to take place. And in this case, it is hydrochloric acid plus ammonia, which is again our weak base and strong acid, HCl. Going to produce some NH4 plus and some Cl minus. Once again, you can, if you choose to, keep these together as NH4Cl. So if you want to, or you could split them off just so you can see each part of it, which might be a good idea. Obviously here, since we're starting our titration, we do need to do this ice table in moles. And again, I'm just going to make up my numbers like I did last time. So I'm going to say not that, because that is wrong. We are actually, in this case, we are starting with the weak base, and we're actually adding this guy. So I'm going to start with my 4 moles here of the NH3. And once again, because we're before the equivalence point, as we talked about last time, and with the other titrations, the equivalence point, everybody's equal. And before we get there, whatever we're adding is going to be less moles than what we started with. So in this case, making up the number, we'll go with 2 moles. Just like we talked about last time, we do know that it is the smaller number here that's going to be the change. So we will use an actual number. And at equilibrium here, I got nothing going on. I got 2 moles here, and I do have 2 moles here. At this point, as we talked about a number of times, you do want to make sure you kind of convert back into molarity. So we're going to take both of these guys and divide it by liters. And again, that should be your total volume in this case, and that's going to convert these into molarity. By the way, I ignored the chloride here because, yeah, it's a neutral solid. So again, in this situation, not going to do anything. Maybe just don't put any number there for sure. Um, what you have left at this point, if you're not sure, again, you can look at your ice table. We have NH4 plus, and we do have NH3. That again is a weak base and is conjugate acid. If you put the chloride back with it, it's the salt of its conjugate acid. And that hopefully should ring a bell to you that this is a buffer. So very much like the previous one with the weak acid and strong base, before the equivalence point here, you will again create a buffer. The difference is you're going to create a basic buffer at this point. Do you have a question? You can. So that's the one place where if you are going to use Henderson's block, technically speaking, you can go in with moles. I again would just recommend just always kind of converting it to molarity, because if you're not going to Henderson-Hasselbalch, you're going to need molarity for other calculations. And if you get in the habit of just kind of rolling with the moles, if you don't adjust it correctly at the end, you're going to get sort of the wrong answer. But it will work out correctly in the Henderson-Hasselbalch equation because you're dividing those and the volume cancels out. Yep. Yep. No, so if you could recognize it as a buffer, because a buffer is a common ion, that's basically what the Henderson-Hasselbalch equation is for. So you should always be able to use it. You could use it in a acidic condition, basic, any type of pH condition. It should work. Or you alternatively, you can't always do the ice table without the Henderson-Hasselbalch. But if it is a buffer, you should be able to use the Henderson-Hasselbalch equation. Yep. Yep. Other questions? So as was just talked about, Henderson-Hasselbalch, probably the way to go here. And again, you just want to make sure you get obviously the base in the right spot and the acid in the right spot. By the way, in a titration like this, you probably have the Kb value given to you, so you might need to convert it into a Ka or a pKa. You also could use that kind of POH version of the Henderson-Hasselbalch equation we saw as well, and use the pKb if you wanted to, but remember it is flipped. Alternative, you can do an ice table, and you actually have a couple of options in terms of ice tableness of what you want to do. You could just do a weak base ice table here. And you can use the Kb value. Again, you would need an initial molarity here and an initial molarity here in order to do it. You could also do a weak acid with NH4 plus on the other side and use the Ka value as well. So there are a few different ways that you can do it. But once again, probably the Henderson-Hasselbalch, a little less room for error if you do it. So this is very similar to the second titration we talked about with a weak acid and a strong base. Again, we're going to have a buffer here. So just like we did there, we're going to create the buffer. And frankly, we're going to blow through the buffer at some point. And that, again, in this case, is why we see a good drop to the equivalence point. Because, again, we are adding acid, so the pH is coming down. So we see that drop happen to the equivalence point. So let's talk about what happens at the equivalence point. So in this type of titration at the equivalence point, again, we got our reaction happening, our NH3 and our HCl. And again, I'm just going to kind of separate these out, but you can definitely, if you want to keep it together as ammonium chloride, you could. This is what we are starting with. This is what we're adding. And once again, this does need to be in moles. So if I use my makeup for moles here, because we're at the equivalence point, we should know that we should have an equal amount of moles of the acid that we're adding. These are going to be 0. change here. You can't pick the wrong one, hopefully. And it is 4 moles in my example. And we're going to end up with 0, 0, and 4 moles here. Once again, we're going to convert back into molarity using our total volume. And again, I'm really ignoring this because, again, it's neutral, so it's not going to do much there. At this point, we do see we basically have a salt left over. And this salt really is ammonium chloride. And because obviously this guy here comes from NH3, which is a weak base, this would be as conjugate acid, and it would mean it will go through hydrolysis. So we will need a second ice table here. And once again, because it comes from a weak base, it will act as an acid, which means when it reacts with water and goes through hydrolysis, it's going to donate the H plus over. Remember that in a hydrolysis reaction, it always makes where it came from, so it will make NH3, and it will make H3O plus in this case. And once again, because it's making H3O plus, we would expect our equivalence point pH to be acidic because we're producing H plus ions basically in solution. This again is where we're going to use our equilibrium concentration and stick it right in there as our initial. And once again, this table is going to be zeros and X's. This is going to go into our Ka value. Remember that we are producing H3O plus. So once again, you most likely will have the Kb for your NH3. So you're going to have to use your Kw there to convert it like normal. And obviously, when you do solve for X in this case, it actually will equal the H plus concentration. So that will get you your H plus concentration, and then you could go into your pH. So again, very similar to the second type of titration we talked about, you will form a salt at the equivalence point that will go through hydrolysis. And because that salt comes from a weak base, it will act as an acid and will produce H3O plus in that solution. And you would again expect our equivalence point in this type of titration to be acidic. So a reminder that the 3 types of titrations we have talked about so far, strong acid, strong base, will give you a neutral salt at the equivalence point, so you expect the pH to be 7. A weak acid, strong base, you will have a salt that will go through hydrolysis that comes from a weak acid, will act as a base and produce hydroxide, so we expect it to be basic at the equivalence point. And here, a titration of a weak base with a strong acid will give you a salt that came from a weak base, which means it will act as an acid and produce H3O plus, and you would expect your equivalence point to be acidic. These are important things to think about, for example, when you want to choose an indicator as to what one would be a good one to choose. So if you're doing this titration, you probably don't want an indicator that's going to change color in the basic range because that's way before your equivalence point is going to be. So these are things you want to kind of think about. Any questions on that there? All right, so that brings us to the last part of this titration, which is step number 4 there. And step number 4 is, again, after the equivalence point. And again, you're going to get your reaction of your weak base here. And we're starting with this guy, and we're going to add our hydrochloric acid that we are adding. Going to make NH4 plus and Cl minus. So because we are adding, obviously we're going to do moles. So we got our 4 moles. Once again, because we are past the equivalence point, we're basically just dropping in the HCl at this point. So once again, we have an excess amount of HCl, a limiting amount there of NH3, and we should have more moles of what we're adding than what we started with. And once again here, always want to pick the smaller number. So our limiting reagent is going to be the NH3 in this case. And we will end up with here 0.2 moles. and 4 moles in this case. Once again, converting it back into molarity. And we can see at this point in the titration, we have NH4 plus and we do have HCl. Again, hopefully you could recognize that this is not a buffer as they are not related to each other. We have, again, a salt that will go through hydrolysis and act as a acid. And we also have HCl, which is definitely a strong acid. So between the two of these acids, just like we did in the other titration, at this point, once you cross over the equivalence point, we're going to ignore the contribution of the salt, as the major contributor to the pH is going to be our strong acid that's left over. And because that is a strong acid, that basically will be your H plus concentration, which means you're good to go basically right into the pH at that point, and you could get it, which obviously should be a acidic pH. So this type of titration curve is essentially identical to the one that we talked about last time in terms of the 4 parts. Yes. It would be, because really the major one is going to be that HCl, because again, the HCl basically just has to do this, right? Kind of like when you do a titration, right? You just keep dropping it in. So as soon as you drop it in, it's going to break apart and produce a lot of H plus. Remember, this guy, he's got to go hunt down some water, right? Do a little reaction. That's like a reversible reaction, right? So not going to go all the way forward to begin with. So it's not going to produce anywhere near probably the amount of H plus in that solution than just having that HCl just keep dropping in there. So that's why you definitely want to ignore it at this point. And that's also why, for example, at the step before that, the equivalence point, we don't ignore it, because at the equivalence point, we don't have any excess HCl. So really, the only thing in that solution that's kind of creating H plus at that point is the salt. Other questions? So as I was saying, basically this titration is exactly the same as the weak acid strong base titration, except that it's upside down. So at the very beginning, instead of doing a weak acid problem, you're doing a weak base problem. At the before the equivalence point, you're doing a buffer problem. At the equivalence point, you're doing a hydrolysis problem. And in this case, at past the equivalence point, you're doing a strong acid problem as opposed to a strong base like you had in that one. So they're very similar type of calculations. Any questions on that there? All right, well, fun with titrations. All right, so take a while here, and we want to figure out what is the pH at each of these steps along the way here in a titration of 100 milliliters of 0.1 molar nitrous acid is titrated with 0.1 molar sodium hydroxide. We want 4 different spots. What is the initial pH of the solution before we begin? What is the pH after you added 80 milliliters of the base? What is the pH at the equivalence point? And what is the pH after you added 105 milliliters of the base? The Ka value there for HNO2 is 4.5 times 10 to the minus 4. Yeah. All right, so work on it for a bit. I'm going to take a nap, and eventually I'll wake up. Then we'll go through the different parts. But use this time wisely. Made a dent into some of these here, and let's see. All right, so obviously we're doing titration here. Good to identify maybe what's going on. So I see a Ka value, so that's probably a weak acid. And sodium hydroxide is a strong base. So once again, this is a strong base, and we have a weak acid. So weak acid, strong base titration. That should give us a titration curve that, you know, kind of looks like so. Yeah. So before we begin, part A, the only thing that we have there is the weak acid. In this case, we are, again, adding the sodium hydroxide to our weak acid. So we're adding that there to our HNO2. So at the very beginning, the only thing that we do have is the weak acid. So part A is before the titration begins. So we got 0.1 molar nitrous acid with a Ka value of 4.5. times 10 to the minus 4. So because it's a weak acid, we do need to do basically a weak acid problem, a Ka type problem. So we're going to take our weak acid and we're going to dissociate it up into a little H plus and some nitrite there. Our Ka expression here going to be H plus times NO2 minus divided by our HNO2. And obviously that equals the 4.5. Because we have not really started the titration, we can do this table again in molarity because we're not mixing volumes or anything like that. So this is going to be a 0.1, a 0, and a 0. This again is going to be a table with x's, so minus x plus x plus x. That means at equilibrium here, 0.1 minus x, x, and x. Any questions on the table so far? Like normal, we're going to try to solve for x here. So we're going to pop our stuff into there. That's going to give us x squared divided by 0.1 minus x equals 4.5 times 10 to the minus 4. You can assume x is equal to 0, but because you are professionals, you know the check is bad, hopefully, because it's 6.7%, and that is over 5. So here we cannot do the assumption because it is over 5. We do need to solve it, obviously, quadratically, and that means we just got to do a little bit of distribution here. So we're basically going to multiply everything we got there on the bottom to the other side. That's going to get us here, x squared is equal to 0.000045 minus 4.5 times 10 to the minus 4x, bringing everybody to the same side. Going to get us x squared plus 4.5 times 10 to the minus 4x minus 0.000045 equals 0. That's going to be our A, B, and C here for our quadratic. Popping that into our quadratic here, which I think I did on the paper. Going to get us x is equal to minus b, which is 4.5 times 10 to the minus 4, plus or minus, if you do everything within the square root, you will end up with 0.000, I think, 1802. And if you square root that, you will end up with 0.0134. And that's going to all be divided by 2 times a, which is 2. That's going to yield me 2 x values here. It's going to get me a x value that is 0.006485 going the positive way, or the adding, or a negative value of negative 0.006935. In this case, we could see from our ICE table that H plus equals X. So clearly here, the negative number would not be a great choice there. And that means that this is going to be our H plus concentration going into our pH minus the log of 0.006485, going to give us an opening pH here on our titration of 2.19, looks like. Yeah. Any questions all about there? So again, a weak acid problem here because we haven't started, and obviously we have a weak acid here. Also a good reminder, make sure you do check your assumptions, as they may not always obviously work. Any questions there? All right, so we were kind of sketching our little curve there. We got like a 2 there happening. Actually, we got 2 happening there because we have 0 volume. All right, now part B, we want to know what is the pH here once we add 80 milliliters of the base. So obviously we are going to start our titration at this point. We're going to get a reaction, so 80 milliliters of our base. So in part B, we have 100 milliliters of our 0.1 molar nitrous acid, and we're going to add 80 milliliters of our 0.1 molar sodium hydroxide. It obviously is the same weak acid, so we'll use the same Ka value, 4.5 times 10 to the minus 4. So here we are going to get the reaction between these two. So little HNO2 going to react with some sodium hydroxide, a little acid-base reaction there, gonna make some water here, and perhaps a salt in this case. Since we obviously are adding here and doing our titration, we do need to do this in moles. So we are starting with this guy and we're adding this one. So in terms of our initial moles of HNO2, actually, not 3, 2. We're going to go 0.1 for the volume times 0.1, going to give us 0.01 moles. For our sodium hydroxide, we got to convert it to liters, so 0.08 liters times 0.1, going to give us 0.008 moles here, and 0 going on here. So am I before, at the equivalence point, or after the equivalence point? I should be before. Again, the moles of what we're adding is less than what we're starting with, besides the next thing says at the equivalence point. But so we're actually before the equivalence point here. That should be a really important piece of information for you because you should know what type of problem you're going to end up with. Let's see if it is that. So at this point, this is still going to be our limiting reagent before the equivalence point. That's going to be our excess reagent as we want to choose the smaller number, 0.008 moles minus 0.008 moles and plus 0.008 moles here. That means at equilibrium, we're going to end up with 0.01 minus 0.008, 0.002 moles. We're going to end up with 0 there and 0.008 moles. At this point, we want a little total volume action. And obviously, we started with 100 milliliters of our acid. We added 80 milliliters of our base, so we're at about 180 milliliters total volume. That's a big titration. And we're going to divide by 0.18 liters, which is obviously what we were looking for here. And that's going to get us here 0.002 divided by 0.18. Going to get us 0. Minus 0.008. Get us 0.0111 molar. And over here, 0.008 divided by 0.18, gonna get us here 0.0444 molar in this case. Any questions on that so far? All right, so we can see what we have left, hopefully, is these two guys right here. And again, that is a weak acid. That would be its conjugate base or the salt of its conjugate base. And because we're before the equivalence point in this type of titration, we should expect it to be a buffer in this case. And it is. And that means we can use our Henderson-Hasselbalch equation at this point. And we are going to get the pKa value by taking negative log of 4.5 times 10 to the minus 4 minus the log 4.5 to the minus 4. Going to get us a 3.35 pKa. So putting that in here, 3.35 plus the log of our base, which obviously is this one here, and 0.0444 by 0.0111 here. And we will end up with about a 3.95 pH in this case. Yeah. Any questions on that one? Obviously, you could also have done a second ice table if you want to instead of the Henderson-Hasselbalch. So that should hopefully be good since we are increasing. So we started at like a 2-ish, so now we're like at 3. So our pH is at least going up along the way here. Next spot is the equivalence point. And again, we obviously have a reaction taking place at the equivalence point, and we have 100 milliliters of our 0.1 molar nitrous acid with our 0.1 molar sodium hydroxide here. And we are obviously still using our same Ka value there of 4.5 times 10 to the minus 4. In this case, they do not give you the volume to reach the equivalence point, so you do need to figure it out at some point. Again, in this case, because the reaction between HNO2 and NaOH is a one-to-one relationship in terms of stoichiometry, you can use M1V1 equals N2V2 and solve for V2 in this case. V2 would be M1 0.1 molar times 100 milliliters for our acid divided by our molarity of our base, and our molarities will cancel, and you will need 100 milliliters of your sodium hydroxide to reach it. If both the acid and base are the same concentration and it's a one-to-one, you need the exact same amount of volume to get to the equivalence point in this case. Other ways you could get it is, you know how many moles you should have, right? So you could use the molarity of the base and the moles and figure out the volume as well. So that's another way to do it. So let's do it here. We need a little ice table action here, HNO2 plus our sodium hydroxide, giving us our water and our salt. Once again, we're going to do this first table here in moles. So obviously, we got 0.1 molar times 0.1 liters, 0.01 moles. Once again, if you weren't sure of the volume, you should know that these moles should be equal to each other since you're at the equivalence point. And as I mentioned a second ago, if you just want to use the molarity of the sodium hydroxide, you know the molarity, you know the moles, you could solve for the volume there, and it will give you the 100 milliliters. Well, it'll give you 0.1 liters, but it's 100 milliliters in that case. This is going to be 0. Good news is I can't pick the wrong number here, so there's only one number to pick. So we'll go with that number. Yeah. And that means at equilibrium, as we would expect, 0, 0, 0.01 moles. This is why you do need to figure out the volume of the sodium hydroxide so that you could add it to the volume of the acid and know that you are at this point 200 milliliters into your titration. It's probably a big beaker, I hope. We're going to divide that by 0.2 liters in this case, and you're going to end up with a molarity here of 0.05. Any questions on the table here? Once again, you can use the table to figure out what you have left. And again, you should know in this type of titration, when you reach the equivalence point, you do have a salt left. And one thing you should know again is that salt did come from a weak acid, which means it is a hydrolysis situation in this case. It is not the sodium that's going to go hydrolysing. It is the part that comes from the weak acid, the NO2 part there. So this is our double shot of ice table here, right? So we're going to take the NO2 minus, which is the part of the salt that comes from the weak acid, and we'll go through hydrolysis. We'll react with water. And once again, because it comes from a weak acid, it means it's going to react as a conjugate base, which means the Bronsted-Lowry definition of a base is it should accept the H+. Again, common sense also tells you it doesn't have an H to give, so it can only accept in this case. By the way, again, it always makes where it came from, so you always have kind of where it came from. And in this case, it is going to produce a little bit of hydroxide here. So once again, we should know that this is going to be a basic pH like we would expect in this case. And we're going to carry down the molarity here. And again, why it's important to convert into molarity, because if you roll with moles and don't do a correct adjustment at the end, you're going to get the wrong answer. So just roll with the molarity. This is going to be 0.05 molar. This is going to be just a regular sort of ice table with X's. 0.05 minus x, x, and x. This is going to go into our K expression, which again is our products divided by our reactants. And this should be a KB, yes. So remember, it should be a KB because we're producing hydroxide here. We do not have the KB given to us, but we do have the Ka value given to us. So again, we do need to convert it. So that is where we could use our Kw. So the Kb, I'll just do it right here in the center. It's going to be 1 times 10 to the minus 14 divided by our Ka, 4.5 times 10 to the minus 4. And that is going to be a lot of 2's, 2.2 times 10 to the minus 11. Now putting into our expression here, we're going to end up with x squared divided by 0.05 minus x is going to equal 2.2 times 10 to the minus 11. We could assume x is equal to 0 in this case. And if we do that there, I was going to flip the page, I think. We have x squared 0.05 minus x is equal to 2.2 times 10 to the minus 11. Assume x is equal to 0. Going to get us x squared 0.05 equals 2.2 times 10 to the minus 11. We're going to multiply first, and then we're going to square root. Yeah, so we'll go 0.5 times that, and then do a little square root. That's going to get us an x value of 0. That's a lot of zeros there. I'm not counting right now, so we'll go with scientific notation here. 1.05 times 10 to the minus 6. We do want to check it, so here we would divide by 0.05, times it by 100%, and I think we should be pretty good. There's not even 1%, so the check is good in this case. That does equal a reminder, when you look at the ice table, that equals the hydroxide concentration, again, not the H plus concentration in this case. So that's going to be our hydroxide concentration. So that's going to allow us to go into our POH, which is minus the log of 1.05 times 10 to the minus 6. And going to get us a 5.98 POH. And obviously, we're just going to take 14 minus that to get to our pH, which should be basic, hopefully. And that's a pH of 8.02 in this case, which is, again, what we would expect at the equivalence point in this type of titration because of that salt being there, producing the hydroxide. Any questions on that there? That's also higher than our last point, which is also good. So our titration curve is taking shape. So I don't know, we're up to like 8-ish at this point. So we're kind of rolling through, coming up. So we're going to come this way at this point. All right, last one here, which is part D. What is the pH after we add 105 milliliters of the base, which clearly is probably going to be after the equivalence point. So 105 milliliters of our base is added to our 100 milliliters of our acid. So obviously we still need an ice table here, so we'll do that. And we'll do our moles, so our HNO2. And as you can see in this example, and most examples that you come across where you have multiple steps, you do take each step as kind of individual. like you started at 0 and just opened it up to that volume, and you started at 0 and opened up that volume. It's not like a continuation of the volume usually. And you'll end up with 0.01 moles for our sodium hydroxide, 0.105 liters times 0.1 molarity, 0.0105 moles here and 0. Once again, this is what we're adding, and this is what we started with. Once again, what we're adding is more moles than what we started with. So again, that also should tell you you are past the equivalence point in this particular case. Because of that, again, in this case, the acid is going to be the limiting reagent because it is the smaller number of moles. So we're going to subtract the acid in this case. And we're going to add the acid to this side. That means at equilibrium, we'll have none of the acid left over because that red color phenolphthalein did not stop you. You just kept going. And now we will have 0.0005 moles and 0.010 moles. Obviously, at this point, we're at a total volume of 100 milliliters plus 105. That's a 205 milliliter total volume. We're going to divide everybody here by 0.205 liters to convert them into molarity. And that's going to get us here 0.002439 and 0.01 divided by 0.205. That's going to get us 0.04878. At this point, again, if we look at our ice table, we got sodium nitrite and sodium hydroxide left over. A reminder that that is not a buffer, right? So even though you get two numbers, this is not a Henderson-Hasselbalch situation. This is a salt that will act as a base, and this is a strong base. Knowing that you are after the equivalence point, that should remind you that this type of titration, this is the part where we ignore the contribution of the salt. And because this is a strong base, that means that this is the hydroxide concentration, which means we could go into our POH minus the log of 0.00243 going to give us a POH of 2.61. Subtracting our 14 to convert it into a pH will give us our basic pH here of 11.39, close to the magical 12 number. If you were titrating, you could almost be done at this point, right? And again, that is what we should expect since we're just adding base at this point, and we should be pretty high at pH at this point because we're just dumping a lot of base in there. Question on that part there. And that would put us up here in terms of our titration, probably up in this area here. So you need to be able to obviously calculate the pH anywhere along these three types of titration curves. Any questions on that there? All right, we will lay it up there.